So the next section in chapter 13 is about solids, and it starts off with an interesting picture. This is a big deal. This is a buckyball, and the original name of the scientist that discovered it was Buckminster Fullerene, after an architect and interesting individual called Buckminster Fuller. Um, and these are carbon atoms, even though they're yellow. These are supposed to be carbon atoms. And there's an alternating hexagon, pentagon shape to them. Buckminster Fuller was an interesting character. I'll put this in the chapter credits. This is a little more scientific about these buckyballs. They kind of look like soccer balls. He developed the first large architectural structures in the dome shape. He felt that this was a more structurally sound and could use less materials. He was a really interesting person. So if you get a chance, watch them. If you don't, it's fine. Nanotubules and stuff with carbon and making really strong, high-strength fibers has come out of this discovery of buckyballs. Whoops, don't like that. There we go. All right, so how are the structure and properties of solids related? Solids are pretty organized, some of them more than others. The particles are locked in place and they can't move around. So they still have kinetic energy, though. That's something I need to emphasize. They are still moving. I've noticed it's not on here, but they're not moving around. Okay. Melting point's the temperature when a solid becomes a liquid, and of course freezing is when the liquid becomes a solid. So, and again, we have a real fixed image in our head of freezing being the freezing point of water. It's not necessarily. Anything that's solid is, by definition, frozen. Doesn't have to be freezing cold. Also, another thing that people don't think about is that the freezing point and the melting point are the same numerically. Water freezes at 0 and water melts at 0. And so if you want the coldest water to put your soda in at a barbecue or a picnic, you want a mixture of water and ice. All right, crystals. We don't have time to do this. It's really not part of the standards so much anymore, but it's still interesting because people like crystals. The shapes of crystals are determined by the lattice, their repeating organized pattern of stacking together. And this is a representation of the sodium chloride crystal, salt crystal, and how they alternate positive and negative sodium and chloride ions. How a crystal looks macroscopically when it gets big enough for you to see depends on how those particles are arranged in the solid itself. There is a huge branch, and of course if you're interested in geology, this is a big thing, of material science, chemistry, not just geologists. Pay attention to this. Galena is a beautiful mineral. I usually would pass around a sample, but there's different what we call crystal systems, and there's actually more than 7, but this is good enough. Cubic is just like the name implies, like the salt crystals. You can evaporate some table salt, water, and look at them with a hand lens. It's pretty interesting. They are little cubes. Same with galena. Tetragonal and orthorhombic are some other shapes, and there's all these formulas. There's a lot more to this, but I just want to run through it really quick. And then there's monoclinic, triclinic, hexagonal, and rhombohedral. So your geometry comes into use, and those are the other of the main 7. The smallest clumping of particles to give that geometric shape is what's called the unit cell. We did talk about face-centered cubic and body-centered cubic and closest packing, hexagonal closest packing previously. So this is a little bit different than that, but similar. That crystal lattice repeats, and there can be different kinds of unit cells in each crystal system. So simple cubic, body-centered cubic, face-centered cubic, and then there's hexagonal closest packing, which they didn't have on that particular slide. So I'll ask you to watch this crystal video. It's relatively short. Allotropes are when you can have the same element, but in different arrangements. And the most important one for our purposes, and then the book mentions, is carbon. So they have different properties. They're all carbon, but because of how the atoms are arranged, they have different properties. And there's not that many elements that have allotropes, but carbon's the most important. So diamonds are in a really interesting arrangement. Of course, it makes it super strong, naturally. Graphite, which is what quote-unquote pencil lead is, it literally rubs off onto your paper because they form in sheets. And then the fullerenes that I mentioned before in nanotubules, those are the 60 plus carbon atoms arranged in little globules and different characteristics, still the same carbon atom, but those 4 valence electrons, it can bond all different ways to the others. So I'll have you watch this one, also under 5 minutes. It's pretty good. Last, of course, is amorphous solid. Doesn't have any morphology, has to do with structure, bodies. They don't have any real organized internal structure. There's no pattern you can observe. Things like rubber and plastic, asphalt and glass are considered amorphous solids. And glass is a product of inorganic stuff, mostly silicon dioxide, that gets rigid without crystallizing. So again, crystals don't have to be sparkly and see-through, but crystals are just organized, regular repeating patterns of their atoms and molecules. And that ends section 3.